Today I'm hoping not to have you the entire time, so I'm sure all of you will be upset about that. But I gotta finish one other thing than what we're doing on Monday. Where I stop is very important because from there on after, notice there's like 50-some pages in these notes. I'm not going over all of them. I'm also not testing you on all of it either. Okay, so there's some notes that I had in a previous programming languages class that we just did other stuff. We don't do that here. So again, you're going to also need to know where we stop, because the rest of it is not your problem. Let's put it that way. Okay? So last time that we had talked about an attribute grammar, which is a step up from the normal context-free grammar that you and I talked about probably about 2 weeks ago now already. Okay? Is that we have to add some other items called semantic rules and or some predicates to really be able to kind of have the grammar work for us with having some steeper checks. So think of it basically as a grammar on steroids that's supposed to make our lives easier. Now notice I said the word supposed to. Okay? What we talked about last class is actually there's two tools that a grammar, specifically an attribute grammar, uses. It uses synthesis and inheritance. The only one that we really went over last time was synthesis, and I honestly don't remember how far we got, so I'll need your input here in a moment. But synthesis is where you actually build a tree first that matches the syntax, and then collect data on the way back up so that we can check it to make sure it turned out okay. Or, if we don't have any type of checks, it probably did something mechanically behind the scenes, like, I don't know if you remember the calculating the decimals last time in the video that I had. It's something mechanical that it's trying to do. So, that was synthesis, which I'll go over here in a moment. But the other one we haven't talked about was inheritance. Now, all of you have been through programming, so you should know what inheritance means. So that's the good news. The other good news is usually it's data that's not very complicated, meaning it's just a simple variable that needs to be passed down as, and here's the important note, as we are building the tree. Now remember, synthesis is the tree's built, and now we start collecting data on the way back up. With inheritance, as the tree is being built, that's as inheritance starts passing down further and further down with information. So that's the difference between the two. Now, I'm going to ask you to bear with me on this. I'm trying to draw a lot of things out for this last set. And the screen, while great at times, sometimes it's not. Let's put it that way. So it may take me a little while to draw it out. But that's the only way that I can really show you what the answer is. Because here's something you need to write down in your notes right now. The solutions that I give you for either synthesis or inheritance shows you the finished snapshot. And if you look at the two, it looks exactly the same. You're going to look at me like, what's the difference, Lupoli? And I wouldn't blame you. So I have to draw out how exactly this is done step by step so that you can see the difference. Because the book pictures don't give you that. They just give you the snapshot at the very end. And again, it looks exactly the same. So you won't know what the difference is. So that's why I'm going to need your patience on getting things, well, so that you can understand it. Let's put it that way. So, last time, I think, and you're going to have to help me with this, we got to this question, I know, but I don't remember if we went over an answer. Did we go over an answer yet for that one? I'm going to say from the complete silence, that's an absolute no. Okay? All right. So here's what I want from you on this. The steps were there when, frankly, we had class last time. I'm actually trying to give you most of the answers already. Number one, start with the grammar. You're going to design what the grammar looks like. I give you the answer with the trees that are underneath. The answer's not hard. Don't make it hard. Number three is what data members do you use in the grammar notes? Yes, I know, I skipped two. Think about it as a programmer. All of you are either in data structures or have been in data structures. if you were to pass information in a linked list, what data members would you use in order to pass that information? Don't make this hard either. 2 is the one that kind of sucks. You've got to figure out what is the algorithm on collecting material on converting a binary value to a decimal value. And there's a very, very specific way of doing it with this tree. There's not a ton of answers to this. So 2 is going to suck. 1's going to be easy. 3, you got to think about it. Let's put it that way. Okay? By the way, your number 3 might be different than somebody else's, and that's okay. So that's what I want you to work on for right now. We'll go over answers here in a little bit. I want to give you about 5 to 7 minutes. So let's say it's 1:58 right now. We'll start back up at 2:03. But I want an answer. If you don't get it, try. I want you at least to try something. If it's wrong, so what? It's not like I'm testing you on. So don't get stuck. At least try something. You go from there. All right. Get to work. All right. So, as I'm sure you know, the 11001 equals 25. Okay, now, how do we get to that? So remember, the syntax rules that are at the bottom, not the semantic rules, but the syntax rules came from the chart that I already gave you. That should have been part number 1. That should have been the easiest part, because bit really only has 2 options, which is 1 and 0. Okay, so bit only has 2 options, which is 0 and 1. But b-val also has 2 options. B-val had an option where it just went to bit, and that's when it only had that last digit or that last bit. Most of the time it went to b-val and bit together as a grouping. So you have actually 2 options for both rules. And that was number 1, and that part I hope you got, because honestly, if you didn't, you need to see me, because that part wasn't meant to be the hard part. The rest of it sucks, especially if you look at the semantic rule for number 1. If you didn't figure that out, I don't blame you. That was a tough one, but we'll go over that here in a second. So I first want to start off with your number 3. Your number 3 asks, what data members would the nodes have in order to transmit the data basically through the tree? You only needed 1 in this one. Now some of you may have done 1 or 2, and that's fine. But you only really needed 1, and that was the .val. So I want you to circle that in your notes. That was the only data member that every single node had that was able to transmit the data from bottom to the top. That was it. Okay? Bless you. Now, after that, I'm going to the map that you have on your top right side. Just give me a moment here. There we go. Now, what's happening here is I'm going to try to draw this, so bear with me here. Okay, you see it on your screen. It's good. That's the rule number that I'm using. That's a syntax rule. So notice, by the way, I didn't use number 1. Why? Why did I not use syntax rule number 1? And honestly, it's an easy answer why. So don't ever think this.
We didn't need to create a new b-val?
Sorry, buddy?
We didn't need to create a new b-val?
That's correct. We didn't need a new b-val. All we had was basically a digit, and that's it. So that's why we have our rule number 2 is using the bit. Okay? So once we get 2 done, go ahead and get our calculation done, and then I go ahead and transfer the data from 1, basically from bit to b-val. The value 1 physically transfers, and there's that 1 right there. Okay? So that's how we're transferring information. This looks very similar to what you've done with nodes before in C++ and objects. Okay? From here on out, though, I need to start using rule number 1. That's because every time I have b eval that's going to be basically grabbing information from two sides. One was from a previous b eval, which will always be listed as number 2, which is right here. And then your number 1 to the side. So remember, we did this before. This will always be index 1. This is always index 2. This is, could be 3 if it's the same digit, but notice these are named exactly the same. So this was called b-val, take a corner, and b-val. So that's how I can get away with that. Alright? So notice from there on up, I'm going to be using rule number 1 because I have 2 places of information that I need to store and calculate. That's how we get away with using the semantics rules. Now, again, this portion right here is used to do the actual calculation from bit to decimal. Again, if you didn't get that, fine, I'm not worried about that. But understand how I got the index number 1 and how I got index number 2. That part's the important part. Okay? Now, from there on up, we're just going to be doing the exact same thing. So notice, this equation is the exact same thing as this equation here. It just has values to it. That didn't come from God or osmosis or whatever. That calculation came from the semantic rules. Okay? Last part. I know I show it here in the drawing, but I am physically calculating this from the bottom up. Meaning I had to create the tree first, and then I could do the calculation, which frankly you're most used to. That part you're used to, especially in this class. Okay, questions, because this is the time to ask it. Do we have any questions?
So the first index is this one?
The first index, it depends on the, notice that I used rule number 2 for that very bottom one. And notice number 2 doesn't have anything about index numbers. And that's again because there's only one instance, this is b-val. There's only one instance of b-val. As soon as I move away from that, then there is more than one. So that's why I have to use number 2, and that tells me the 1 and 2 separation.
So that's the whole grammar, those 4 lines?
Yes.
That's the whole grammar?
That's it. That's it. Yeah, now, don't, and make sure I'm trying to keep it simple. So I'm not trying to make this ugly. So you're going to see much uglier than this. But I'm trying to keep it simple. Okay. Any other questions? Great questions. Okay. I want you to do one more. You're using the same grammar. I'm giving you basically the answer. What I want from you is basically a repeat of this table right here. But you're going to do it for a different syntax. That's it. You're also going to tell me what rule numbers, what the equation did, all that stuff. You're basically going to repeat it with a different set of values. That's all I'm asking. You're going to need to draw it out. I don't care if you do it in paint or pencil. You're going to need to draw it out, though. Right? And then we'll go over it together. Your new set of numbers is this. 1, 0, 1, 0, 1, 1. Again, you're basically drawing the tree first. 2, then you're going to start telling me what rules you're using. And 3, you're going to show me how you calculate it. I know you can easily convert that to decimal. Tell me how the tree does it. So bear with me on this, but this is super important on how synthesis works because again, the only thing that you see in your notes is the final setup. And again, that doesn't really show you how the step-by-step works. So I'm showing you what I have on my screen on your screens, but notice how things are going to change. And again, it's also going to change or have a different setup when it gets to inheritance. So far, all of this is synthesis. So that means I had to build the tree first, and then I can start having the values start coming up through it. So, if I'm at the very, very bottom, so I'm looking at this, what is the only syntax rule that'll match with that? It's rule number 2. So you notice I specify and then I give the actual number of the rule. Everybody okay with that? Now, rule number 2, all it basically says is, hey, move the value from bit up to b value. What's the value of bit? It's 1. So I'm going to move 1 up to here. Everybody okay with that? Now here's the bad news. This is where things change. Now, as you know, as you're solving the tree from the bottom up, you know that dreaded computer science cuss word called recursion. You know I don't need bit anymore because I transferred that information up, now we're moving up. So I'm redrawing this line. Now which syntax rule moves or uses this?
2 or 1.
It's 1. Okay, you had a 50-50 shot. Look at that. That is syntax number 1. Okay? Now, in syntax number 1, it's going to look for the value from a previous b-val and then the digit. Now remember, does anybody remember what index this one is?
1.
That's 1. This is index number 2. And then we have digit or bit. Sorry, she said digit. Meant bit. Does that fit exactly the semantic rule for your syntax number 1? Answer is yes. Now again, if there was something different, then we'd be in deep doo-doo. Okay, so it had to be an exact match. Now, I'm going to use, notice I'm specifying which one, rule number 1. Now I'm going to do my calculation. Somebody's got to help me. I'll look up your screen here. All I'm looking for is actually the calculations here at the end. So, matter of fact, I had it right here. Duh. All right. So, b-val of 1 equals, change the color or anything. B-val of 2, which was 1, times 2 plus 0. Everybody know where I got that calculation from? From semantics rule in number 1. It did not come from the heavens. So, if we do 1 times 2 plus 0 equals 2. Everybody okay with that? Alright, pray the eraser works. So if I'm done with that, I move up. Hey! No. Alright, what rule am I going to use for this one? Give me number 1. What's the calculation going to be? Well, this one is going to be what? 2 times 2 plus 1, if I'm not mistaken. Okay? That equals, last time I checked, 5. Are we okay with that? That makes that 5. Doing some erasing again. Why not? This one. Okay, what rule number that is? Number 1 again. Okay? 5 times 2 plus 0. But again, remember, we're getting at zeros. Not inventing anything. So that equals 10. We're good with that. Doing some more erasing. Why the... This thing. Bad when you gotta punch a $25,000 monitor. But man, it feels so good. Alright, I think this was 10. Was this 10? It's gonna remind me. Yeah. Alright. So 10 times 2 plus 1. Same rule again. Number 1. So at the very end, let's see here. I should have, that's the 10 times 20, 21. So that should be 20 times 2 plus 1. So is the answer 41 at the end of all that?
43.
43?
It's 21.
Oh, it's 21. Yeah, thank you. Yep, 21. So that makes it 42. Yep. Thank you.
Yeah, she's not one in there.
Everybody okay with that, Joe? Ugly but true. Notice how, again, I went from the bottom up to get that information, just like you would normally solve a tree. Just like you normally solve a tree. But it was a hell of a lot of work, to say the least. Especially for me, you just sat there. Yes, sir?
When does our indexing start at 1? Like you said, math.
Great question. I don't have an answer for you on why it's 1. I know I would have thought it would start at a 0. I don't know if this is an author thing or whatnot. So
like, if we wrote our own grammar, could we call it like 0, or does it have to be like 1 is apparent?
the only thing that I could think of is that they may want to have a temporary spot. In data structures, we use a temporary spot that we know what it's going to be, that we use. So it might have left 0 for that temporary spot to add everything into. So that's the only thing I can think of right off the top of my head. But yeah, now remember, you would do this in a compiler's class. And normally in a compiler's class, they kind of give you a little bit more free reign. But as you know, more free reign also means more that you can. Yeah, you're prone to error too. So, but I understand your question. It's a great question. Why it's 1 and not 0? Didn't tell you off the top of my head. It could also be author's precedence, which wasn't me. But okay. Great question. All right. Got a new one for you. This is the last one. Thank God. Because I know this is not fun either. My next one is inheritance. Now, the weird part is, it's easier to show you how inheritance works because of how you and I have already gone into inheritance when it comes to programming. The interesting part is that the author of your book decided to do a solution that actually has both. It has synthesis and it has inheritance at the same time. So you should be on page 22. So here's how this works out. Actually, hang on, let me scroll down a little bit further. So notice, it's still going to be about the same syntax. For the number of A's, you need to match a number of B's, you need to match the same number of C's. The part that gets interesting is 2 things, and I want you to change 2 items that are on this, because as a matter of fact, during the break here, I looked at the book and there was a difference, meaning this. So give me 1 second. I want you to put in syntax rule number 2, somewhere on there, say that this one is using synthesis. A is using synthesis. Now there should be there should be some type of dead giveaway on that. There should be. Anybody know what it is? There's a dead giveaway in the syntax rule number 2 that it is using synthesis. It's not the left arrow, because there's other left arrows in 3 and 4. It is in that section with the left arrow. It is the +1. Because remember, at the bottom, you start off and then you keep adding as you go back up. Okay? So that is your synthesis portion. Now here's the weird part. The other 2, B and C, are inherited. And notice it subtracts 1. Now I'll prove that to you here in a minute on how that exactly works. But it's using a mix. A is first synthesis, and then B and C are inherited. So how does this work out? Let me show you. First I gotta find my drawings. Alright. There's my beautiful, beautiful Picasso drawing. In the example, like I said, first it's going to actually start off with the A's. and it maps the A's. So we have all three A's, and notice that when we start with the bottom one, our size is equal to 1 because we only have one A so far. But as we travel up the tree, our size increments each time. And I'm sure you figured out that's okay. Here's the weird part. To make sure that the other ones follow suit, and that they only have n number of repetitions, they use inheritance. So what you'll see is that in your syntax rule number 1, which is actually on the big screens above you there, it's going to pull the size from A, which is 3, and then assign it to say, hey B, now you're going to do this 3 times. So B the first time, so you can use another color here. Yeah. You know, let's do this one. So the first time we get to B, we're given an option. Inside of rule or syntax rule number 2, we either said B if it's equal to 1, or we have B and then we have our B sequence. So it's B, our B sequence, or I'm just going to put it as BS, that's perfect. Now, at this time, our size is equal 3. Because again, it got the 3 from here. Now, the next time we call BS. Keep my day job, I know. BS. Now what's my size going to be? It's 2. Now how did I decrement it? If you look at the syntax rule for number 3, which is B, notice there's that subtraction of 1. Makes sense now, doesn't it? I want you to change one other thing that's in the notes. Where the highlighted blues are, where it says in size and then B sequence equals 1, put a double equals in there. Put a double equals. A lot of people are thinking that that's assigning the value of 1. It's not. For some reason, he used double equals in a previous example for comparison and then didn't here. I know it says first B is set to 1. That's true if you're checking to see if it's the last one. So that's just saying that that last B is going to be 1. So that's the last one that we needed. Okay? But the rest of it, notice there's an OR after that. Then we have our B sequence B. Okay? Now, I then move down one more. One more call to BS. B size equals. So notice how first, when we did synthesis, our tree or our parse was built first, then the value was pushed up. Now that we use inheritance, we use that same value, and notice that value ended up changing, kind of like a recursive function, frankly, until it finally ended. Okay? But once we got it to 1, that was it. We're all said and done. Everybody okay with that, though? Do we have any questions on it? Okay. Now, real quick question. Take a look at C, or rule syntax rule number 4. Is that going to use inheritance or synthesis? Which one? Talk to yourselves about it first, quietly, and figure out why. So what's syntax rule number 4 going to use? Synthesis or inheritance? Inheritance. Okay? Because again, notice that every time a value is, not just because it's decrementing, but it's updating, and frankly, you know it's already been given the count. So you know that's going to be inheritance. You know, one of your classmates also brought up a great point. If you look on your screens, I have 3 A's, 4 B's, and 3 C's. And she asks a great question, wait a minute, what about that 4th B? She's absolutely right. Now, how do we stop that from making that 4th B is actually in that predicate that I asked you to edit a little bit. Remember where it says predicate for B, and it says inside B squared double equals 1? Notice, it's that or something else. Once I hit 1, I stop. There's no other calls. There's no other parse rules. There's nothing else. You just stop. That's why it's called the predicate. It's because there is our base case. As soon as I get to 1, I stop. So there's no way that I get to this last part at all. No way I get to it. Again, that predicate says, hey, if it's equal to 1,
Stop.
it doesn't say stop, but it also doesn't give you any other options. Let's put it that way. Okay, thank you for following up. Here's the other part I want to ask you. What data member is the nodes using? What data member are the nodes using? There's just one. Now remember, that data member is going to be throughout all of them, and it's keeping track of something. And it does have a name, a very specific name. What is it? Again, there's only one of them. Who's got an answer for me? Who's got an answer? Yes, sir.
The data member size?
Yes, it is. It's size. Now, funny part is for A, it's actually called size. For B and C, it's actually called in size. So that's the weird part. So notice the difference between the two. Now, it looks like a function. You're right. It's probably the same thing as your isEmpty that you would have in a stack or a queue or something else that would return the size of what the list is. Okay? But it's still basically a data member that's going to be retrieving a value. That's it. Okay. How are we on that? Any questions to that? Okay. Actually, we're almost done, right? 2:40? Okay. We'll leave it at that. Okay. So again, from there on down, you're not responsible for it. So right about there. Page 25 on down, you are not responsible for. I'll see you on Friday. Friday's a good day. Make sure that you go over the videos, the exercises, all that stuff. Friday, you can be out of here in 15 minutes if you do a good job. Otherwise, you might get stuck right off the bat. So make sure that you do some good work for Friday. See you then.